In this video, we are going to do an example where we pick n+1 integers among the first two n positive integers. So the example says, prove that in any set of n+1 positive integers selected from the first two n positive integers, so I'm picking n+1 integers from this set that starts at 1 and then contains all the integers up until 2n, that there must be an integer in that set that divides another integer in the set. Okay, so I first want to play around with this for about 2 minutes, and I want to try this for a specific case. So what if n equals 5? If n equals 5, then the last integer in the set would be 2 times 5, which would be 10. So I'm picking from the set of positive integers between 1 and 10. And if n is 5, then n+1 would be 6. So I'm going to be picking 6 integers from this set. So I first want to have you try just picking 2 different sets of 6 integers from this set, and just show that in whatever set of 6 that you pick, that there's an integer in that set that divides another integer in the set. So try that for about 2 minutes. Pause it in 4, 3, 2, 1. Pause it and try it. All right, so hopefully you did that. Hopefully you paused it to try it. So let us talk about this. So let's say that the integers that we picked were 10, 8, 3, 7, 5, and 9. So I noticed that in that set of 6, 5 divides 10, and I see another set where 1 divides the other. I see that 3 divides 9. So in fact, in this set of 6, there were actually 2 pairs where within the pair, one of them divided the other. Okay, and hopefully when you were trying this in whatever set of 6 that you picked, this was happening as well. Okay, so how do we solve this and show this in general? So there's some key ideas. I want to show that there's 2 integers with some property. The property being that one of them divides the other. So if I'm trying to show that there are at least 2 integers with some property, this language is a tip-off to try the pigeonhole principle. That's one of the indicators that I might be trying pigeonhole for this. So since I'm picking n+1 integers, these are probably the pigeons, and I want to show that there are 2 with some property, well, I need more pigeons than I have holes. So if I have n+1 pigeons, I'm probably going to have n holes, or as long as it's n or fewer holes. Okay, that's key idea 2. The third key idea is, well, whatever the holes are, I'd really like it so that if there ended up being 2 things within the same hole, I would just be done. So what it would take for that to happen is I would really want all the elements in a given hole to divide each other. Or at least, if I pick any 2 of them, for one of them to divide the other. So in any pair, one divides the other. So that's what I mean by that. In any 2 that I pick, one of them divides the other. Okay, so how can we do this? Let's do some scratch work first. I would first want to play around with it in the case where n equals 5. So, I really want to think about what these holes are. I know the pigeons are these n+1 integers, but what are the holes? So I first want to give you an opportunity to pause it and try it. This is often the hardest part of pigeonhole problems, thinking about what are the pigeons and what are the holes. So I'd really want to give you a chance to think about that first. Pause the video for 5 minutes to try that. 4, 3, 2, 1, pause it for 5 minutes. Okay, so hopefully you did that. Let's bring it back and talk about it. So in this first hole, I'm going to place the integer 1 in it. And then I'm going to double that to get 2, and then double that to get 4, double that to get 8. If I double that again, I'd get 16, but that's now outside of my set. So I'm going to stop it there. And if I do that, I'm going to make this be hole 1. Because if I take any 2 things within this hole, like 2 and 8, well, one of them divides the other, because of how I constructed it and just kept doubling and doubling and doubling. one of them is going to divide the other for sure. So in my next hole, I already have 2 is in the first hole, so I don't need 2 in the second hole. Let's start the second hole at 3, and then let's double it to get 6. And then if I doubled it again, I get 12, and that's too big. That would be beyond 10, so I get to stop it. This is going to be hole number 2. And even if I pick 2 things in this hole, like 3 and 6, well, one of them divides the other. So great. In the next hole, well, I don't need to start it at 4 because that's already in something. So let's start at the next odd integer, 5, and let's double it to get 10. So this is going to be hole number 3. And again, if I pick 2 things in this hole, one divides the other. Okay, and then continuing this pattern, let's start the next one at 7. I can't double that though, because that's beyond 10. So this next hole only is going to have 7. The last hole then is only going to have 9. This is going to be hole 4. This one's going to be hole 5. I don't need to go to 11 because my set of integers stops at 10. So I wouldn't have 11 as part of it. So overall, there are 5 holes that we have constructed here. So I want to observe that since we are picking 6 integers and there's 5 holes, and there are 5 holes, at least 2 integers, two integers will be in the same hole. And that's great for us. That's exactly what we want. Because if there's 2 things in the same hole, no matter which hole it is, whether it's this one or whether it's this one, well, one of those things will divide the other. Another thing that we might notice is, well, there's no way for these 2 things to be in hole 4 or hole 5, which is totally fine for us. Like, that doesn't hurt our argument in any way. That just means, well, it would have to be in hole 1, 2, or 3, but whichever hole that they're in, they're going to do it for us. One will divide the other. Okay, so we have the key idea. Now, how do we formalize this in the proof? So first, I want to give a theorem for this key idea we were observing about, this starting with an odd thing and then keep doubling it. Any positive integer n can be written in the form 2 to the k, so a power of 2, multiplied by m, where m is odd, and this exponent is a non-negative integer. So a power of 2 times something odd. So for example, 32 could be written as 2 to the 5 times the odd integer 1. Or 60 can be, I can divide it by 4, which is 2 squared. And then what's left is the odd integer 15. So 32 would have been part of the whole that starts at 1. 60 would have been part of the whole that starts at the odd integer 15, if n was big enough to include that. Okay, so I'm going to put this theorem in a little thought bubble, and now we're ready for the proof. So in the proof, I start off by stating what we're given, which is I'm going to let a1, a2, comma, dot, 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 up until an+1 be positive integers in my set that consists of 1, 2, 3, comma, dot, 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 up until 2n. So then by this theorem, then I can say that all of these positive integers can be written in this form. So a1 can be written as 2 to a power of 2, like I'll call it 2 to the k1, times an odd integer, which I'll call m1, comma, a2 will be 2 to the k2 power times m2. Notice I'm using different variables for these because the a1 and a2 are different. So these powers are not necessarily going to be the same. These odd integers are not necessarily going to be the same. Comma, dot, 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 up until the last one is an+1 would be equal to 2 to the k subscript n+1 times m subscript n+1, where the k1 up until kn+1, they are all elements of the non-negative integers z greater than or equal to 0, and m1, comma, dot, 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 up until mn+1 are, running out of room here, they're all odd. Okay. Okay. So I want to notice a couple of things. I want to notice that these integers that I'm selecting, they're going to represent the pigeons, and there's n+1 of them. And the wholes are dictated by these odd factors. So, if my set consists of 1 up until 2n, how many possible odd factors are there? So I want to notice that the odd factors, m1 up until mn+1, they have to be elements of, what are the odd values within the set? Well, the smallest one is 1, then there's 3, then there's 5. The last odd number would be the one before 2n, which is 2n-1. Okay, so there are, if we count these, there are n of these. There are n values, n possible odd factors within this set. So I'm picking n+1 pigeons, placing them into these holes here that are dictated by those odd factors, and there's just n possible odd factors. So now we're ready for pigeonhole principle. So I get to say by pH, by the pigeonhole principle, at least 2 of the AIs have the same odd factor. I'm going to call the odd factor mi. So in other words, there exist an AI and AJ. Let's write that a little bit better. AJ such that AI is equal to 2 to the ki times mi, and AJ has to have the same odd factor, so it's also going to end in mi. It might have a different power of 2, so let's assign a different variable to this one. 2 to the, I'll call this ki tilde to indicate the power may be different. In fact, the power has to be different because the a's have to be different from one another. These a's are distinct positive integers. Okay, so then is one of them going to divide the other? It turns out, yeah. It's whichever power of 2 is bigger than the other, that's going to dictate which one divides the other. So I have two symmetric cases depending on which power of 2 is bigger. So I can use without loss of generality. So I'm going to say without loss of generality, let's assume that ki is less than ki tilde. Then we can divide the bigger one and do aj divided by ai. That'll be equal to 2 to the ki tilde times mi over 2 to the ki times mi. Now the mi's will cancel, and I'll get 2 to the ki tilde minus ki. And this is an integer. Since the exponent ki tilde minus ki, that is a positive integer. This is a positive integer because we assumed ki tilde was bigger than ki. Okay, so that means if I move ai to the side, that aj equals ai times 2 to the ki tilde minus ki, where this thing in the parentheses is an integer. So because aj equals ai times an integer, thus, this means that ai divides aj. And that's exactly what we wanted to show. So we are now done with the proof. And there we have it.